Okay, once you compile the gene package, you can do some simulations. So the simulation that most used for me is read from the experimental data. So here is a parameter file. Basically, almost everything that you need to change is here, unless you want to change the profile, which we'll talk about that later. So here is basically way to parallel. So if you have certain amount of the processors, you have say 512, and then you need to distribute it into certain ways, like species, velocity, W, X, Y, and Z. And then here's a grid. Here's basically how many processors you want distribute them, and this is how many grid or definition in a sense of those parameters. And there's a lot of parameter that related to to that, and also there's like ls, ky min, x not center. So for more details, I strongly suggest you to read the gene manual, which has a relatively comprehensive explanation to those. Since this gene is written in Fortran, the exclamation mark is the way to comment things. But same time, but if you have exclamation mark and immediately after you have a scan list, then actually it will read this line. Basically, what Scanlist does is basically scan, instead of just one simulation, it will scan through on multiple variables with the respected simulations. For instance, this one will be 1, 2, 3, 4, 5, 6, 7, 8, 9. There will be 9 different values for 9 different simulations. So you don't have to submit 9 different jobs. You can just scan it in this way. And the most of the time what you need to change is the directory. You need to change the directory to the directory that you want your output to be at. For NERSC and also for almost all the supercomputer, you need to put all of those into a scratch directory. And also in the input, either DB file, which is the input of the like profile, basically temperature, density, pressure, and the rotation or shear. And this is basically, do you want to read from the checkpoint? Basically, you can, if there's a checkpoint system, you can like say like this simulation is not done. You can read, like, see, I wanted to write the checkpoint. It's writing the checkpoint, but if my simulation is not done, I can change this from F to T, so that I will have I can read from the checkpoint. So here is the step of each parameter. Pretty much in a sense is if you change everything to 1, basically every single time step of evolution, if you're using an initial value solver, if you record every single step, the output file will be enormous. So basically, what this means is every 100 step, it will record, give you a record, so that you can use that. So sometimes you want higher resolution to do, say, a synthetic diagnostic or Fourier transform. You want to change it to lower numbers so that you can have a higher time resolution. And for this, for the current problem, you don't need to worry about. Let's first just talk about eigenvalue solvers. All of them are pretty much okay, and sometimes if it doesn't even converge in the time that once it reached the limit, it still doesn't converge, you can increase that, of course. A -1 in gene basically means it will it will read from the original profile. So -1 basically will read those numbers from original profile, and all of those quantities are not normalized to SI or nor GSI Gaussian unit. They are normalized to gene unit. You wanna, I think in the future I will have a video specifically for the gene unit, but just keep in mind, and also you can check them on the gene manual. So for this, we're doing magnetic. So I changed that, and hyp Z and hyp V is a hyperdiffusivity. Basically, I would consider that as a buffer. If something just very, very rapid and highly localized, you can, or even sometimes numerical, you can use this as a buffer to damp out some numerical instabilities, or even the instabilities that happens physically, but you don't technically want. Sometimes ETG that you don't want, you just increase the hyperdiffusivity to damp out the ETG. And here's you need to have it aside from the iterdb file, you can have to input a G file, which is a geometry file, which contains the real physical geometry of a device, and also the magnetic field information. Sorry, like background magnetic field information. And edge op is basically, I didn't enable it. Enable it, basically it will optimize such that in the midplane or the center or across the horizontal across the center has a higher definition for some purpose. For instance, that you're only interested in the middle around the midplane. And this is the plasma current and the magnetic field orientation direction. For this specific simulation, we're doing 3 species. So we have all 3 species: ion, electron, impurity. So all of them are basically set as such. You don't need to worry too much. -1, you just read from the original profile, unless you want to change something, which I will talk about later. This is basically run through of each block, what each block means. You have mass. The mass of the in the parameter file is normalized to the ion, which is deuterium. And as you can see, the mass is here. The mass is 2, and this -2 is, I think, is pretty much means you read from the profile. And all the units and reference, you can just read from the profiles. -1s, and the mref is 2, basically 2 proton mass, which is deuterium. And for local linear, you don't necessarily want the E cross B shear. You can just comment this block out so that you don't have E cross B shear, but keep in mind, then you won't get, then the simulation will be in plasma frame instead of lab frame. Then you need to translate it into a lab frame manually. And this is output, direct output, and they will tell you how many you need to scan, and we have 9 different quantities to scan around, and it says there's the output, where the output gonna be. So for things like in this matter, you can check on my GitHub account, which I will hopefully I remember to put into my into the description. This in the research public gene parameters, I have a whole list of parameters. Is Basically, those acronym LL stands for local linear, LN stands for local nonlinear, and the NEO stands for neoclassical, GL stands for global linear, GN stands for global nonlinear. EVs. So far, what I've done is local linear eigenvalue solvers, and also a read from tracer, basically read from analytical models, and also I have a list of scripts such that it can make a gene profile, profile that you can as an input instead of reading directly from the profile. You can construct your own profile, your own analytical profiles. And here, so let's assume that everything here is exactly what you want. You can go to the gene, cd gene, and this is in the terminal. Most of them are running in Linux. You can learn such language online. There's a lot of useful material. I will cover the part that I think is necessary. So the easiest way to create any is just /new probe, and it will create a new probe called probe 01. Then it has almost everything that you need to run it. And for us, I prefer using some realistic simulation data. For instance, I can just go with this. So I have everything I need, and I have the geometry file, which has a background magnetic field, and a real device specs, and we have either DB file, which is a profile file, and temperature, density, and such. So we need to modify the submit file, which is basically tell the supercomputer how long I want to run it, and how many core I will request. So here it is. So you can request it for different machine. It has different name, different project name, different conventions. For NERSC query, we have this. You can use regular. Basically, for regular, you have full access to how many cores and how many hours you want. But for if you want to, but it will take a long time to queue. Basically, say if you submit this job, it will take maybe 1 day or 2 days to queue. But if you just want to know if your code works, you can change it to debug. But debug is fast. You can just get it almost immediately, run immediately. But same time, you only limit it to for NERSC, you are limited to 30 minutes. For tech, you are limited to 1.5 hours. Actually, let me see. Do I have a better edit with? Okay, well, I'll change that. This is a new computer. I need to change something. Anyway, so for scanning, you need to do this, like scan script, yada yada, and this is how many cores, and you request a node. Each node, number of node, each node have 64 64. This I forgot to change it. It should be 64, 64. 1, 2, 3, 8. Okay, yeah. So this is a scan file, and if you only run one simulation doesn't scan, you need to run this as run. Basically, you don't need to scan it. You don't need to operate this scan script. You just need to go with this script, this line. Actually, a good thing to notice is that I have everything here. You can see that I have the scan or not scan, so you can see the difference. See, as run, this is not scan, and this is a scan. Again, you can check on the GitHub repository so that to familiarize to make yourself familiarize with it. Let's get into this directory, just for the sake of testing. You just type s batch, and then the file, this command file, submit knl.command. You can enter tab to autocomplete, and then you should type enter. Then it will submit the job, and this is the number you can keep track on. And I can see SQUEUE -U max query. So you can check if it's running or like if it's complete or how what status it's in. See, it's complete, and it's running for 12 seconds. Just so you know, this is complete not because it just finished running. It will take much longer than that, but rather because of there's some inconsistent code. You can worry about that in later time. This is an introduction of how the whole thing, how to run it. And in the future, I will talk about how to run the diagnostic and how like what each segment means side by side. This is just a general, quick and dirty run through on how to run the gene. And also feel free to give ask the question in the comment section.